today's talk that because last week y'all gives us a talk about Binius, kind of I think the content also the papers are very dense. So today my talk is kind of talking more about the theory part, and I think we should go through from very basic ideas from the binary field, and then the why we need the recursive the extension tower. The extension tower. Then we introduce the tensor algebra introduced by Binius we can easily to embed multiple small field value into one big field. And then at the same time that we can use the big field for security, seeing that the verifier can sample a big field value for a challenge. At the same time, the prover can commit small field values for building polynomials and prove the properties of polynomials. So this is the third part, tensor algebra. Okay. I think all three topics kind of involve too much math. So let's just begin with the first binary field. What binary field is, and some basic ideas, basic concepts that are very important for us to understand the tensor algebra. Okay. This talk I just try use the Python to write some code. If you install already installed the Python Jupyter Notebook, you can follow me. And it's okay for just don't code and let me just code everything, and and check if you can understand. Okay. Okay. So the Python language that I use is quite simple. If you don't understand, use your hand. I will explain more details for you. Okay. So first of all, the Binius introduced the binary field, which is very different from other modern Ziggy-Star systems. But yes, the original Fry used the binary fields. But the Binius, the differences between Binius and the original version of Stark are that Binius utilized rich mathematical structure or algebraic structures inside the binary fields to do more optimizations over that. So let's just get started with a very simple basic idea. So if you can follow, please raise your hand. I will explain the details. Otherwise, I will quick overview all the basic concepts. Okay, the first that because I use Python plus CGMath, we can easily define, for example, a prime field. Looks like this. Can anybody see the code? Yes? No beta, yes? Yeah, good. Thank you. The idea is simple. So we just use CGMath. It's a CGMath function, GF, short for Galois field. And then we can define the F7, and then we can list all the elements from F7, like from 0 all the way to 6, right? So that means the F7 has 7 elements in F7, okay? All right? And also the number 2, sorry, the element 2 is a very special element inside F7 because 2 is a so-called primitive element. So F7, sorry, probably not. F2. Yes, let me try. Okay. F7 to I for I in range 7. Okay. Yeah, 2 is not a primitive. Sorry, I'm sorry. It's a random guess. Oh yeah, 3 is the prime element of F7 because we can get all the elements except the 0 of F7 by multiply 3 by itself again repeatedly. Then we will have all the from F7 except 0. Okay. 1, 3, 2, 6, 4, 5, 1. And 1, why? Because the 3 is seventh roots of unity. Sorry, it's our 6th. Yeah, 6th roots of unity of right. That's the reason why the 3 is the comments here. 3 is primitive. It's a primitive element.
I think you shouldn't use the first
sorry?
element for I because the first element for I is 0.
Yeah. Yes.
So there are 2, 1.
Yeah, I just because it is a cyclic group, so we can from anywhere.
Yeah.
Just repeat, multiply any elements by 3, then literally we can get all the elements. Okay, it's a prime field. It's a prime field. And then now we're trying to. So what is a binary field? So the simplest binary field is F2, because also 2 is a prime number. So we can build F2. So F2. So there are only 2 elements in F2, 0 and 1, right? And in F2, we can do something like this. So, 2 in F2 are actually equal to 0. Please remember this. Okay, 2 is 0. And what about the negative 1? Okay, it's actually equal to 1. Okay. Now let's define a polynomial ring over F2. Call it R2, and introduce an indeterminate named x0 equals to F2. So it's kind of so now we define F2x. Okay. 0. Okay. Define 0 and show R2. Okay, R2 is the polynomial ring, univariate polynomial ring over F2 with the symbol x0 as the indeterminate. So now we can define polynomials over F2. For example, 2 squared plus x plus 1. Okay, it's a polynomial, right? It's a polynomial. polynomial, then yeah, it's polynomial. Sorry, x0, so 0. Okay. We can evaluate this polynomial by, for example, we just let x0 equals 1, then we can evaluate. Sorry. What will happen? So, this one. Sorry.
This
Yeah. Okay. Now we can evaluate the polynomial over F2. Okay. And then we can also multiply two polynomials. For example, x plus 1 times x0 plus 1. Okay. It equals to x0 squared plus 1. Why? Because the cross term equals to 0, right? So if in a if for the polynomial over integer, that x plus 1, when we calculate a square, we'll have this x squared plus 2x plus 1, right? But here, please remember that we're not in the world of binary field, so there's no 2. 2 actually equals 1. So then we have x0 squared plus 1, right? Okay. Okay, this F2 looks like very naive. So now let me introduce an extension field of F2, so called F4. So F4 is not a prime field because 4 is a composite. So we can easily define that field, F4. Okay, F4 is a finite field in Z2 of size 2 squared. So now we look at the elements from, enumerate the elements from F4. Use the list function. Now we get this one, something weird, Z2. So what Z2 is? Okay, Z2 is a new symbol that was added into F2 to make sure we can build a matrix over F2 to represent F4. So F4 is a so F4 can be not so rigorous, like a warning, not rigorous. So here two. For example, if one t in F4, t equals to a tuple with 2 elements from F2. How can I say that? T0, T1, where T1, T0 in F2. Okay, F4 is we can see every element in F4 is actually a tuple, a pair, where each of the component is a F2 element. So now we can list all the F4 elements like this, like 2 pairs 0, 0, 0, 1, 1, 0, and 1, 1, right? We can use the pair of bits to represent every element in F4. Here we saw this somewhere, the representation. So what the relationship between that actually it's an inner product. Okay. Actually, we have such F4 basis equals to 1, Z2. And then each F4 element actually is a bits representation, do some inner product with the basis. Then we get the actual element of F4. Okay. For example, sorry? Okay, no question? Okay, good. Okay, and then we can we can see the F4 element like a matrix 1, 1, 1, 0 with 1, Z2, 1, Z2, okay. Here's 0, sorry. It's 0, 1. 0, 1. Yes, here the 0, 2, and Z2 plus 1. Okay. So F4 can be seen as a matrix, or in mathematical jargon, kind of it's a vector space with a basis. We just choose basis as 1 and Z2 as the basis to form that matrix. Okay. So right now, F4 can be used as a 2-bit number. So F4 is identical to a 4-bit number. Okay. Even F4 has such, looks, complicated representation, but F4 is identical to all 2-bit number, right? From 0, 0 pair of 0, 0 all the way to a pair of 1, 1. Okay. Okay. Any questions so far?
I don't understand that. People.
Okay, this will.
Yeah. Actually.
Okay. Yeah. Okay. Probably it's not correct, but.
I think the table might be the vectors. Element should be the vectors, and you might.
Yes.
Multiply the matches to the the basis vector.
Yeah. Yes. Yes. Probably I should remove that part to make sure. Okay. I think it's easier to understand this expression, right? The basis is kind of a 1, Z2, and then we can do the inner product of 0, 0, pair of 2 zeros with 1, 0, Z2, then we got 0, right? Then we do inner product with 1, 0 with 1, Z2, then we got Z2, right? Okay. Okay. Good. Now in Binius, which is we want more bits number. For example, 16 bits number or 32 bits number. Now we define 4 bit number F16. Okay, F16. F16. Oh, sorry. So F16 First of all, we have one approach, just like the approach that we used to define F4. That we use the GF function provided by SIGMath to define the F16 with 16 elements inside. F6. Now we can look like all the elements inside. Oh, looks like this, you know. But Z4 kind of not easy to read. Now we just use some SIGMath feature to use another symbol to redefine this one. Now, we just use small a, the symbol to represent something, to make sure that we got all the elements of F16. And we can say that, each element of 16 looks like a polynomial. Actually, it is a polynomial. So why we need that? Because F4 is a matrix, right? F4 is a matrix. It's a matrix or a vector space. It's easier to define addition over matrix, over a vector space, vector, right? Because it's just the entry-wise addition, right? For example, F4, for example, can easily define, for example, a plus 1 plus a square plus 1. Yeah, we can see, it's a square plus 1, right? It's an entry-wise addition. So because F16 is a field, so field has another operation of multiplication. So if F4 or F16 is a vector space, now how can we define the multiplication over this extension field? So the multiplication is defined by the polynomial multiplication. So we can easily to see this. For example, let's do a simple multiplication. A plus 1 times a plus 1. It's equal to a squared plus 1. Exactly the result from the polynomial multiplication we did before, right? Yeah. But the polynomial multiplication is not the whole story, because when we multiply two polynomial, the result polynomial, the order of the result polynomial will be sum of the operands, right? The degree of operands. But you can see that in F16, the highest degree of this element kind of equals to 3, only equal to 3. So how about we multiply these two elements together? So what will happen? So for example, a to square plus a times a to cube plus a plus 1. So what will happen? So if the multiplication is a polynomial multiplication, we'll get a polynomial with degree 5. But the result polynomial is not element of F16. So we need something like so actually the result kind of still a degree 3 polynomial. But this element is the inside F16. So let's check. 3, 2, 1, 1, 2. It's here, right? So multiply two elements in F16, we got another element in F16. So the truth is that the multiplication over extension field is a multiplication of two polynomial, and then we do a modulo operation, modulo some polynomial. So let's check this modulus. We can call this function to show that, okay, we have this one. A to 4 plus a plus 1, exactly the polynomial that we multiply these two polynomials, then do the modulo over this polynomial, then we get this result, right? Okay, then we can check if we are correct. So we use the polynomial ring. I need I need define another ring. Sorry. X, sorry, y equals to F. Okay. Then let me check. Y squared plus y times y third plus y plus 1, and then mode y 4 plus y plus 1. Okay. Now we can have this polynomial, right? Exactly same. The result of two field multiplication of two field elements. Okay. So far, any question so far here? Okay.
Why is the F-section polynomial
So why now use y symbol to just to illustrate this polynomial?
My question is on the search line. Why
30 here?
Why this polynomial is like 31?
Sorry.
Why 39 is the
Y 31.
39? The 39 is
30,
the
30, okay.
Polynomial.
Okay.
Why is this defined like this?
Y is what?
Why it is a square? 就是为什么是这个多项式为什么是？
Okay. So if we define, so the question, the Mark's question was why when I call f16 dot polynomial, why the returns is on something polynomial like this. Okay. Okay, this polynomial is called an irreducible polynomial, and the Sigmass just randomly choose. It's not randomly choose. Just use some strategy that we don't know to pick one reduced polynomial with degree 4 to use as a modulus to generate F16.
So it can also be other.
Yes, we will show later that we have multiple ways to extension field. So just
for constructed for the F 是
sorry.
是为了构造 F
Yes. This polynomial is used to construct F16. Yeah, sure.
So whenever the degree goes above 4 or 5 digits, modulo by this also.
Yeah, to make sure that degree is less than 4.
Yeah.
It's not unique.
Yeah, it's not unique. Yeah, we have, we will say we have 3 different irreducible polynomial with degree 4. Yes. For binary field, yeah. This is one of those. Just one of those.
The 31 is if we take an element of field 16, that is y.
Okay. This is for convenient for me. It's convenient for me to verify if the multiplication plus the modulo kind of equals to field multiplication. So just ignore this weird ring. Okay, just ignore that. Okay, I mean, remove. So temporal, yes. Okay.
So I can basically see the irreducible polynomial, like irreducible polynomial to polynomials is what a prime number is to
Yeah.
integers, basically.
Yeah, not rigorous, but it kind of. It looks like a prime field, prime number. Yeah. Okay. So now let's say that all the elements of F16 except 0 will form a multiplicative group. So then I can show that way. Can generate in range 16. So A is actually A is a primitive element of F16. Why? Because we repeatedly multiply by A, then we get all elements except 0 of F16. Okay? And then also we can have a basis of this vector space, identical to F16. So basis, the truth is we can have many different bases. But we can choose one easy to understand. Okay, this here 1, 0 square and 1 to Q. Okay. Here we can define this basis, right?
Yeah.
To represent all elements inside. Okay. Okay, now let me show you that 0 so all the elements of F16 actually are roots of this polynomial. The polynomial is like x0 to 16 minus x0. So we can factorize this polynomial. We can have a bunch of polynomials. Here we have x0. X0 represents 0 because x0 as a single polynomial, then the only root of x0 is 0, right? How about this one? X0 plus 1, the only root of x0 plus 1 is 1, right? It's 1. And then we have this. X0 squared plus x0 plus 1, this polynomial will have two roots. Will have two roots in bigger field, in extension field. So two roots kind of a and a plus 1 are the roots of this. Okay, let me check. So I have to redefine the polynomial ring of 16. Let me use another y. Okay. We could just y squared plus y plus 1, we factorize this polynomial, we can have, okay, sorry. It's not a2 squared plus a and a squared plus a plus 1 are two roots of this polynomial. Okay, how about this? How about this? How about this? Then we can factorize the polynomial, okay, in the same coefficient. Okay. Now we have a plus 1, a square plus 1. Okay. It seems like random, but it isn't. It isn't random. It has beautiful structure inside. So let me show you. Okay. You can see that this polynomial equals to another polynomial that a minus a times a minus a squared to the minus 2, 4 and minus a to 8. Yes. Okay, actually, so a plus 1, a2 square plus 1, the 4 elements looks like, we can find something inside. But actually, this polynomial can also be factorized into this kind of form. So a equals to a, and then a squared here, and a to 4 equal to a plus 1. And a to 8 is equal to a 2 squared plus 1. And these 4 elements are formed into a special set and has a close relation to a Galois group. But here we don't just go too deep about the Galois theory, but just show you that for each irreducible polynomial over here over F2, it will have 4 elements, 4 roots, and these 4 roots they have close relationship with each other. They looks like brothers, kind of. Okay. So we have this polynomial and this polynomial. These 2 polynomials are irreducible over F2, but can be factorized over F16. Okay. Then we can show that we just factorize this polynomial over F16. We just replace the symbol with y, because y is a indeterminate over F16. Okay, the factor. Okay, we have, it can be factorized into linear polynomial. And now these elements, they are brothers. Okay, they're brothers. Okay. And also this one. Okay, we'll see that this 4 roots and this 4 roots and this 4 roots, they are disjoint. They are disjoint. No overlap. And for each element in F16, it has a unique irreducible polynomial for it. It is called, in mathematical jargon, kind of so-called minimal polynomial. Okay, so when we list all the F16 elements here, then we can calculate each polynomial, minimal polynomial for each element to identify where they come from. Okay. And then if we multiply all this irreducible polynomial together, then we have this universal polynomial. All roots of this universal polynomial are formed as F16. Okay. So far, any question?
So which one is the
I think for example for a cube, a cube, the minimum polynomial is here. Let's say this polynomial. Yeah. Oh, it's just a warning. It's not mathematical rigorous. Okay. Just to show some picture that the algebraic structure inside the binary field and the extension field. Okay. Now okay, no question so far?
Why you can use y to do the factor instead of x0?
Okay, because y is defined is a polynomial ring over F16. And then all these polynomial will not be irreducible over F16 polynomial ring. So that says we can factorize all this irreducible polynomial over F16. So F16 is called the splitting field for these irreducible polynomials in mathematical jargon, kind of. So if a polynomial is irreducible, then if we use the root of this irreducible polynomial and put it into the field, base field, then we have a bigger field, right, called the extension field. Then in that extension field, the original irreducible polynomial will be factorized into linears. Okay.
Can I check the definition for x0?
For what? For
x0.
x0. Okay, x0 is a polynomial ring over F2 here.
Okay. I see.
Okay, x0 is okay. So this polynomial is irreducible in over F2, but it's not irreducible over F16 or even F4. Okay.
I have a question. Maybe one place I haven't catch it. The okay, 39.
30, 39, 39. Okay.
We can say the polynomial is factorization to some polynomials, multiple of some polynomials. And
Okay.
one polynomial, the degree of y is only 1, but y 35.
35. Okay.
Okay, y 35, the multiple of the polynomials, the degree is not only 1, but 2, 4, 4.
Okay. Because we factorize this polynomial, and because some factors of this polynomial are irreducible over F2.
Okay.
So the factorization kind of stopped here.
It can be reduced again.
Yeah, yes. But if we put the polynomial into a extended field, then we can factorize those polynomials.
In field F2, it can be reduced, but
Yes. That's the why. Yeah. Yes. Okay. And then, okay, y2, okay. I think next, let's talk about, okay, here's some, okay. Yes, we can continue. So, because we have, for example, sorry. Okay, over F2, because we have 3 different reducible polynomial, right? And we defined F16 use only one reducible polynomial among the three reducible polynomials. How about 2 others? So now I just define another f16 using different irreducible polynomial. Let's see what will happen. Okay. Let's define this. Let me define another. Okay, wait. Okay, let's define. Sorry, because here. Okay, f16 b b equals to f2 extension x 4 plus x 0 third plus 1. Okay. Yes. Can see that. Yeah, we define another f16, right? Another f16. I should say that this f16 is not equal to the f16 I defined before, but they are isomorphic. They are isomorphic. Let me list the odd element here. Why say that? Okay, the two fields kind of not equal to each other because they have different multiplication rule. For example, here we just multiply. For example, we multiply 2 elements here. Let's say I to square to third. Okay. Then we have a square plus a, right? But if we multiply, okay, the 2 elements from the second f16, now we have this element. So it means that, okay, they look same, but they are actually different. They are actually different. Okay.
That because they use different.
Irreducible polynomial, and the irreducible polynomial affects the multiplication rule. Right? If we use different irreducible polynomial to extend the field, then we got different multiplication. Okay. And then the problem is that so-called embedding or isomorphic. So let me just show how to find the isomorphic map between those two different f16. So this is a critical problem in Binius. That Binius, because Binius introduced the exchange tower to achieve so-called zero cost embedding. Zero cost embedding. I think Yao just mentioned that concept last week. And now show that, okay, the embedding problem is kind of as a critical problem for extended field. Okay. The simple rule, so I don't want to go that too deep. Just give some hints for how can we find the isomorphic map between those two different f16. The idea is that the idea is that we have to find. Okay. So if we build a isomorphic map, that means that the multiplication has also to be isomorphic, right? But they have different multiplication rule. So how should we do is that because a, the minimum polynomial of a is equal to x to 4 plus x plus 1. So just find an element in f16b whose minimum polynomial is same as a. Okay. Okay, let me find any element here is the root of this polynomial. Okay, we just do a brute force search. Okay, because the field is small. Let me evaluate. Okay, y24. Sorry, we cannot use y. I have to define another ring. Okay. Here. Okay, I'll just. Okay. y24 plus, sorry, y24 plus y plus 1 subs t equals y equals t for t in for I in range. Okay. Because B is also a primitive element, then we can use B to I to represent all elements except 0 in F16B. Now we just brute force to put every B to I here into this polynomial, then we say which one is to 0, okay. Okay, sum to be 0, okay. Here is 0, and here is 0, and here I'll go to 0, okay. And now we should create them, okay. Okay, put a tuple here. Okay, good. Okay, we have B to 5, B to 7, B to, sorry, 5, 6, 7, B to 11, 13, and B 14, okay. These two elements are roots of this polynomial. Now we can define the isomorphic map between those two different F16 by using a map from, for example, A maps to B to 7. Then we can have the isomorphic map between those two F16, even they are different, but they are isomorphic with each other. Okay. The other problem is that, okay, so far, let's stop here first. A couple minutes. Any question?
First question, so can you explain the sub S?
Sorry? Where?
Not sub S, so what's the API used for?
Okay, so we just replace y with this. It's an evaluation. Substitute. It's the evaluation of this polynomial. Yeah.
And the B powered by I is a root of another field, right?
B, because B is a primitive element. So
for what? For which root?
for F16B, for here.
Okay.
Right.
So we map A to the roots of
B to 7.
the other
Yeah.
F16.
Yeah, yes. Yes, we can build the isomorphic map between those two different fields.
So you map into all, we also map it to B to the power of 11, 13, and 14.
Yeah. Okay.
So the idea is you find a solution for polynomial and represent by b, right?
Sorry.
Find the root of the polynomial and you represent the root by b, right?
Yeah. Yes. B is the root of this polynomial. But b to 7 is the root of this polynomial.
So the map means each one is the root of different polynomials. So how can we use this map? It means one polynomial can map another.
Yeah, map 2. Because in I can use the whiteboard to illustrate. So in Binius, for example, if the base field is 8 bits, for example, right? It's a byte, right? It's a byte. And then in Binius we can combine those, 4 bytes into a bigger field element. So, but we still want to preserve the multiplication. So saying that at least we should embed this field into a larger field, right? Here, okay. For example, here, actually, it doesn't look like this. There'll be some, it's just simpler example, okay. F4, and then here is F16, right? Then we can have the 4 element here in F16, then we map each element into the F16. In Binius, we commit all the small field. We use small field for the commutation, but we have to use a bigger field for security, for the challenge number sampled by verifier. So we have to do the embedding, right? So, but after embedding, what we want is that to preserve the multiplication in F4, right? So yes, for any F16, sure we can find a symmetric map, but there is some cost because the embedding, we have to do some commutation, right? For this example, we have to do the to 7, right? B to 7 to find. Here is A and here is the B to 7. Sorry, B to 7, right? We have blah blah blah. Now we have to do some calculation between the embedding and the non-embedding. But in Binius, we'll figure out some way that we just map F4 to the first 4 bit of F16. Okay. Yeah. The problem is how can we do that? How can we do? We just there looks beautiful, right? To map them here, here, here. Now we show the example of this one, okay? But now trying to illustrate how can we do this. We just map F4 directly into F16, the first 4 elements. Okay. Okay, let's show you a more direct approach to embed F4 into F16. So now we can see, let's see here. So let's see here. Okay, the first F16. Okay. Okay, just ask you a question. So, which 4 elements can be mapped into F4? Okay, F4 is a subfield of this field. It's not easy, right? It's not easy. But if we can do the factorization, that okay, we can factorize this one. Okay. First of all, and 0 and 1 is the element from F4, but still we have 2 more elements. We have to find the corresponding element in F16. So the operation we should do is we factorize this. Okay. Here we factorize. Okay. The F4. Okay, these 2 roots are actually the elements mapped to F4. Okay, let me write in the whiteboard. Okay. Here map F4. We have 0, 1. A. Okay, let me use U and U plus 1. Okay. Now we define F16. Okay, it's a bunch of elements. But here we found 0 here, and 1 we have the map. But the U map to, I think, yes, A squared plus A. Now U plus 1 map to A plus A squared plus A plus 1. Yes. Now what we want to do is that we find another map or extension, seeing that we can map, okay, put it here, okay, F16 prime. Here we just directly map 0 to 0, 1 to 1. Here we use another, for example, Z, and then U directly map to Z plus 1. Blah, blah, blah. Okay. This extension we're going to show. And now we define F16 directly over F2, so we got kind of a messy embedding. Okay. Is that clear? Okay, any questions so far? Okay, any questions so far? Okay.
How do you know, like, when you're mapping U to A squared plus A, how do you know, like, which...
Mapped, okay.
Yeah,
which one? Or
like, why do you choose x0 squared plus x0 plus 1? Are all
here?
others? Yeah. How do you decide is that?
Okay, because their minimal polynomial equals to y2 squared plus y plus 1. And also, they are also the their minimal polynomials are also the same polynomial. Why we can build the isomorphic map, because they are belong to same irreducible polynomial or F2. Okay, good. Okay. Okay, any question? No, yes, I just show you how can we do that. Okay, do this. Okay. It's called zero cost embedding. Yes. Oh, wait. Okay, where's F4? F4, yeah, F4. Yeah, F4 is here. Okay, let me read. Define view, okay. Let's redefine the 4. So, such that I can introduce a U to. So I don't like Z2 symbol. I just rename the symbol, okay. I can say the okay. The elements of 4 is kind of a U plus 1, 1, okay. That's U. Okay, now. Now we define another F6 V, F16V. We use V as the new element for, we just extend to construct F16 directly over F4 instead of F2. So we define F16 over F2, we use degree 4 irreducible polynomial. Now if we want to, if we define F16 over F2, we just use a degree 2 irreducible polynomial. Extension x0 square plus x0 plus u. Okay. Yes. But here's the problem. So we cannot use x0 squared plus x0 plus 1 here. Why? Because this polynomial is not irreducible. It can be factorized. So we'll have to use, I think, sorry, I have to define the F4 ring. Oh, sorry, where's, yeah, I have to define another. R4 equals to R4 dot x1 equals to F4. And then x1 plus u. Okay. Okay, this is a way different from the extension method from Binius paper, but actually they are almost same. Okay. Not same. I think Binius kind of is compatible with this extension field. F6, another F16. So let me just show. Okay, where's my? Sorry. Here, just list all elements here. Just say, just take a look. Sorry.
X0 times X1.
Sorry?
The line 54, the polynomial should be X1 times X0.
Plus 1, right?
Times X0. X1 times X0. Yeah.
Okay, I don't use that as extension.
Okay.
Okay, the extension you mentioned is presented in Binius paper, but I just use another extension. We have to, for example, just print all. Any term the element in F16B, then we can print T. Okay. Yeah, we can see. Okay, it's totally different, right? F16 V is different from the two F16 we defined before. but they are isomorphic with each other. So if you're interested, left it as homework for you to define isomorphic maps between all three of those. But now we can see here, right? The first four elements exactly the element for map 4. Yeah. Now we just find a natural way to embed a small field into a big field. And then we can continue this extension to define F256 and then larger and larger to build a very big linear field, and then we can use Binius tricks to build these stars. But I think we don't have enough time. In the last, I just show the intuition and why this approach works. Okay. Because we use this extension field, right? Extension field. Okay, we just define F16 as a tuple F2, 4. Okay. I think we use this extension, degree 2 extension, we naturally introduce the structure, a pair. And F4 can decompose as 2F2, right? Okay. I'll show you this. Okay. And then naturally, F4 is the half, is the first common node and second common node of this. And then we can build the extension tower, like the F16 and F16, right? And then blah 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 blah. Okay. But still, we have there are many problems that we have to pay attention to. That how can we find, for example, the reduced polynomial for next extension, or that is there any convenient way to find the primitive element of the extension field, kind of a recursive extension field, or can we give a basis for this recursive extension field? The answer is yes. Yes, we can easily find all of this by using some theorems. So, for example, we can easily define the basis of F16 5 equal to 1 U V and U times V. Okay, it's called the multilinear basis. Multilinear basis for F4s. Okay. And if we build a F256, then we have a similar multilinear basis. And the multilinear basis, okay, it's very friendly for sum check and for multilinear extension polynomials. And yes, then yes, I think okay. Here, so any question about? I think it's kind of the part one of my talk, the tensor algebra in Binius. So, any questions here? Let me check. Okay, any question here? Okay, very good. Thank you for coming.
告诉我什么是 minimum polynomial？
minimum polynomial. Minimum polynomial. 为什么叫 minimum？ 我不是很了解。
但为什么他们俩那个就是 y 方加 y 加1？